Hello everyone, hope you guys are doing well. So the topic that we are going to cover today is to design CAM profiles. And this is very important discussion that we are going to conduct today. So the basic idea is that whenever you're going to perform an automated action based on CAM follower mechanism, the CAM profile is the most important aspect which forces the follower to perform the output motion in a specific way. So that's why it is absolutely necessary to observe the designing process of the CAM profiles. And this is exactly what we are going to cover today. So in previous lecture, we covered quite a few basics of CAM follower mechanisms. And among those different terminologies that were necessary, those were explained. But most importantly, we covered SVAJ diagrams, where S stands for position, V stands for velocity, A for acceleration, and J for jerk. And combining these four, we can say that we have performed the kinematic analysis of mechanisms. So in case of CAM follower mechanisms, SVAJ diagrams serve the basics of the design process, and that is what we are going to discuss in much more detail. If you correlate the discussions today with the previous discussions, you would find out eventually that in the first lecture we spread out this stuff, and in this lecture we're going to get into the details. In-depth analysis will be performed, and this is how we're going to develop a deeper understanding of the topic. So remember last time we discussed RDFD CAM design process, and in that we must recall that R stands for rise, D stands for dwell when there is no motion on the follower, F stands for fall when the follower comes down, and dwell over here again. So it means that you're going to force the follower to rise up, stay there, then fall down, and then once again stay there in the lower position for some time. So this class of CAM follower mechanism is called RDFD CAM follower mechanisms. And by the way, I should also emphasize that sometimes the ordering is going to be different. Sometimes it is going to be like you start with a dwell, then perform the fall, then dwell, and then rise once again. Or sometimes it is dwell, rise, dwell, and fall. So the order of these individual segments is going to be dependent on the nature of the CAM follower mechanism. But in a nutshell, we can say that there is a motion between two dwells. So this is going to be the distinctive feature in RDFD CAM designs. And in that, I'm going to discuss once again the example that we mentioned last time. But on the diagram, you can now see that that you have the independent axis where angle is indicating the displacement of the CAM, and the follower follower motion is indicated on the vertical axis, which is right over here. And in this example, you start with a low dwell, you stay there, you make sure that there is no movement on the follower, then you perform the rising action, which we have not defined, and last time we have kind of drawn in this fashion just to indicate that there is some sort of mechanism to allow the follower to rise up. Then there is this no motion segment once again, what we're calling over here high dwell, and then the falling action is performed to reach to once again the critical point right over here, and then you can repeat the same exercise again and again to perform the DR, DF kind of fashion. This is the starting point of our discussion. And we're going to move on to the velocity side and then the acceleration and jerk side subsequently. But generally what happens is that this is the starting point of designing the CAM profile. So in this example, that we are going to discuss in much more detail in the next slide, you would see that RDFD cam design is being performed. We're going to start from a very simple, straightforward set of selections, and then we're going to gradually build upon those. So one very good example of RDFD cam can be when you wish to perform the drilling operation using cam follower mechanism. So you can assume that there is this cam hidden inside this box. We are not overly bothered about the profile yet, but you just can assume that there is this cam, and in that the idea is that you have a follower head and you have some sort of spring mechanism over here which forces this follower to go down and upwards. So the operation is such that you start with a dwell when there is no motion on the drill bit or on the follower. Then once the dwell has been performed, meaning that you have placed the component just underneath the drill bit, you're free to move to the next stage where you can bring the drill downwards. So this is going to correspond to rise on the follower. Because the drill bit is oriented downwards, so rise over here is going to force the drill to go downwards. So this goes down, meaning that the hole is being drilled when it goes down, and when it is fully forwarded or in the extreme position, you would mean that the requisite depth has been achieved. So at that particular point, generally what happens is that you have another dwell over there. This forces this hole to be drilled in a much nicer fashion, where you have a finished hole as a result of this exercise. So you stay there for a little bit. So this is going to be another dwell, followed by forcing the drill bit to come out of the workpiece, and this is exactly what is going to happen over here as a result of fall action over here. So you can see that this is in a similar fashion that we drew in the last slide as well, that you have a dwell, which is actually in that case a low dwell, and then it was followed by rise, and then there is another dwell which was a high dwell, and which was followed by fall once again. So you keep on doing this exercise in a cyclic fashion internally by making the cam move, and as a result of that, forcing the follower to have a specific movement pattern generated. So this can be one very good example of drilling operation. And by the way, I should also emphasize that RDFD cam is manifested in so many different ways that you would be amazed. This is only one example of those. The other thing that you should also realize that if you force this drill to go quickly or abruptly downwards, there is always this chance of accident over here. So you have to carefully bring the drill downwards. So I'm going to write down over here carefully. And similarly, when you're going to bring it upwards as well, that's also going to be a careful action as well. So when I say the word careful, it means that you have to consider the movement pattern in terms of acceleration and jerk and stuff like that. So this is exactly what we are going to try to cover today in order to perform these actions in a careful fashion. So last time what we did was we connected these extreme points with straight line segments, and that you can see right over here and over here. And we were hopeful that the velocity and acceleration diagrams are going to turn out to be very good, but we were naive. Because when we observed the velocity diagram, we observed that this velocity is trying to change very quickly or abruptly, and that was visible right over here as well as over here. And you can make this observation at these points as well. So it means that the velocity is trying to change very quickly from a low value, zero value, to a higher value, and this was problem sum. And when we observed the acceleration and jerk diagrams as well, we observed even bigger problems where you observed impulses of infinite magnitude over there, which obviously is not going to make this cam profile good enough in terms of the force requirement as well as in terms of the vibrations that it might induce. So as a result of that, we said that infinite acceleration and jerk may not be acceptable, and that's why we were forced to construct the fundamental law of CAM design, and that what we discussed last time. So the fundamental law of CAM design says that the CAM function must be continuous, and continuous through the first and second derivatives as well, and that should be continuous across the entire interval. And the corollary is like jerk should also be finite. And that's the fundamental law of CAM design that we are going to try to observe while making these CAM profiles in the subsequent discussion. So since we observed that the straight line segments are not going to serve the purpose, mainly because the derivatives were not continuous, so what can be the first candidate function to design such CAM profiles? And potentially we may use sinusoids, mainly because the derivatives are going to remain continuous, and also because when the cam rotates and rotates fully, it is going to be a simple harmonic motion that you would observe. So with this realization that we are going to start our discussion by using the sinusoids and observe whether they are going to serve the purpose or not. Let's proceed. So in the start, we're going to focus only on the rise function. This rise function, as described earlier using the sinusoid, is going to take probably this shape, cos of theta, where theta is the angular displacement of cam. And s is the movement or the displacement of the follower. So as a result of that, there is going to be some profile exhibited by the follower. Let's see that how it behaves. This is the result of that. And if I just observe it, I can readily see a few problems over here, because the very first one is like we were focusing on the rise function, but actually over here it is falling down behavior exhibited. So this is obviously problematic, so I need to update it. So the next iteration can be to improve this expression to have an improved version written down. So that would be something like s to be equal to 1 minus cos of theta. So if I exhibit that, this behavior is going to look something like this. And now you can see a change is being shown over here. And this change is right over here. This is a rise function to start with. But the problem that we have got over here is that it starts from 0 and it goes all the way to 2. So in order to have a normalized expression, I need to do something about that. So let's quickly do that. I'm going to say like an further improved version of s can be like 1 by 2 of 1 minus cos of theta. Now, this is going to have a normalized movement of the follower exhibited ranging from 0 to 1, but sometimes this 1 is not going to be the desired displacement. So I should have some parameter which I'm going to control, or any designer is going to have a control of it. So possibly if I write down like h by 2, that would be appropriate. And if now I try to draw this behavior, this is going to look something like that. And readily you can see the difference over here. So from this to this, you can see that it starts from 0, it goes all the way to 10 when h is equal to 10 for the simulation. Now, the other observation that you can make right over here is that of once the rise action has been completed somewhere over here, it then falls down, which may not be needed over here. So I'm going to write down like not needed in this case, because we are only considering the rise function. So as a result of that, I need to have some change incorporated in the expression, and the best way I can do that is to have some scaling factor added over here. So if I do that, s turns out to be equal to h by 2, 1 minus cos of this input argument when scaled to give user control or designer control. This is going to be pi by beta of theta. Now, this is the factor which is going to give some scaling factor because of the beta. So when I try to plot this one, you would see this behavior. And this is exactly what we need over here. And you can see that it is only the rising function that we have exhibited. There is no fall happening, so this is fine. You have control from over this height. You can have any value assigned over here, and you can also see that the range for which the movement is needed to be there, that is also under your control. So now you have got one expression over here which serves the purpose, and this is exactly what we are going to use for the simple harmonic motion. The other thing that you should also observe over here, that in this particular scenario we have started with one candidate function, and we have improved it over here and gradually improved it further and then gradually improved it further in order to give you a better expression which serves the purpose. So you have to kind of have this kind of thinking incorporated as a designer of cam follower mechanisms. Now this is the MATLAB program that I've written corresponding to the expressions that you have seen on the previous slide, and I've drawn them side by side over here in order to make you see the gradual improvement that we have mentioned earlier. So I would advocate that you should try incorporating this program in MATLAB, or if you're using Python, you can develop a similar program over there. But just do try it. It is going to give you a deeper understanding of these sinusoidal functions that we have incorporated over here. Now, the biggest benefit of using sine function, as described earlier, is to have the continuous derivatives. And we're going to take derivatives now in order to see the behavior. So the very first thing that we should compute is that V expression. And if you do that, this is going to be this expression. And over here you can readily see that from this expression that this expression was not having any theta term in it. So that's why this influence is not there in the V expression. And the other expression is quite obvious. You can see that appearing right over here. When you take another derivative, you're going to find expression for acceleration, and this is like very simple straightforward expression. And if you take another derivative, this is going to be the expression for jerk. And obviously you can see over here we have not considered in these expressions like theta to be a function of time, but if we do consider it, so this is going to turn out to be like d theta by dt term added over here, which is going to be angular velocity, and over here you're going to have the square root of angular velocity, and over here you have the cube of angular velocity if you consider theta as a function of time as well. So at this particular stage, we are not considering it because we are only considering the approach of critical extreme points. But if we consider the critical path profile, the other paradigm, then obviously these values are going to be incorporated in these expressions as well. So now moving on, if you plot them, this is going to be their behavior, and you can see these curves on top of each other. And over here, if you observe, what is happening is that the S expression has been translated in terms of this curve. It starts from a 0 value and it goes all the way to the user-defined height of the follower, and it completes the action in a user-defined span, which goes all the way to beta. And when you take the derivative to find out the velocity behavior, this is the curve corresponding to it, and you can see that velocity starts from 0. Over here it ends at 0 as well, and in between you have this curve indicating that how it rises and then falls down. And obviously this expression, because it is the simple harmonic motion that you're observing over here, you can readily see the acceleration expression as well. So it crosses the 0 over here, corresponding to the maximum velocity over here, and quite obviously so. But the problematic area that we can observe is the discontinuity observed over here and the discontinuity observed over here. Because we have said that this is only part of the cam profile. This is only the rise function that we are exhibiting, but actually in a cam profile you're going to have for the one that we are trying over here is RF DF, so you're going to have the other motion segments as well. So when you have those motion segments as well, you're going to have this area to be clearly problematic area, and this discontinuity to be problematic as well. And this further is exhibited when you plot the jerk term, and you can find out the infinite impulses over here, which actually is not at all desired. So in this realization that we have started from the expression for S, and we have moved all the way to velocity and then acceleration and then the jerk, we have seen that that the simple harmonic motion as exhibited by the sinusoids is not serving the purpose, because acceleration is discontinuous and jerk is infinite at a few places. So as a result of that, we can say that it is still a bad cam design. So for the expressions derived on the previous slide, this is the MATLAB program, and you can incorporate this in MATLAB or Python if needed be, but do implement it. It is strongly advised. And then once you have implemented it, try different parameters in it. For example, you can change the height with different numbers and see how it behaves. You can try different values for the beta in order to see how the range changes. And then if omega term can be incorporated in it, so omega terms can be added and see the behavior of a selected angular velocity added to the cam follower system. So that inference can be incorporated in these expressions as well. So you can see the S expression over here, V, A, and J all written down in a similar fashion, and drawn as well over here, A and J. And this is going to exhibit the same observations that we have made earlier in the previous slide. But the point over here on this slide is to give you the syntax corresponding to implementing these expressions in MATLAB, and you can use the inspiration for the Python as well. So after trying the straight line segments for rise and fall, and trying the cosine expression for the rising, and obviously for the falling as well. We have observed that these are not going to serve the purpose. So can we try something else? That's the question. And possibly we can. Uh, and still, I've not lost hope for the sinusoids. One good area that we can try is to use these sinusoids not at the displacement level, but at acceleration level, and then integrating them to find the v expressions and the s expressions. That may potentially help us out. And that's exactly what we are going to do now. So based upon the observations that we have already made, we are going to start with acceleration now. And the expression that we're going to write is this: A is equal to c sine of 2 pi theta by beta. And in that you can observe that 2 pi by beta is the term which is going to scale the input theta to the sine expression. And this coefficient over here is what is going to control the output of this sine function. So as a result of that, and if I plot it as well, I can see that the acceleration starts from 0 value and it goes back to 0 at the end of the specified angular displacement beta. And in between, you can see that it rises up, it falls down, and then once again rises up to go back to the 0 value. So this is the acceleration term that we're going to start with. And in order to compute velocity, we are going to take the integral of it. So when taken integration, you are going to find out this expression. So this is from here to here, when you take the integral of this expression with respect to theta, and this is going to give you this whole expression added with a constant term as well. So with this realization that now you have to figure out K1 as well, you have to see the boundary conditions for the expression. And when you see that, since v is going to be equal to 0, at theta to be equal to 0, when you plug in these set of conditions over here, this is going to give you expression for K1. So now you can use the K1 expression, plug back into the V expression, and V turns out to be this expression. Now this expression is that of velocity, and we can compute the displacement when you take the integration of this. So that's exactly what we're going to do over here. And as a result of that, you are going to find out expression for S. And over here, obviously, there's this K2 term added as well that we have to see corresponding to the conditions for the S curve. And we can obviously find out the values over there. But at this particular stage, the process should be quite obvious that you're going to start with acceleration and perform the integration once to find out velocity and twice to find out expression for the displacement. And in order to find out the expression K2 evaluated, you can see that S is equal to 0 at theta to be equal to 0. So this is this condition right over here. When you plug in these values, K2 turns out to be equal to 0. So you have found out this expression for the displacement term. And when you plug in the other condition, that at theta to be equal to beta, which you can see right over there, this turns out to be, S turns out to be equal to H. When you plug in this value, this is going to give you the other expression for constant C. So this is the other expression. So you should need to plug in these values K1, K2, and C in the expressions for S, V, and A. And when you do that, these are going to be your expressions. And for the jerk, you have to take the time derivative as, or the derivative as you have previously mentioned. With this realization that now you have got the expression for S, V, A, and J already there, you can plot them, and this is going to look like the diagram that you can just now observe on the right side. And over here, the problem that we faced in the previous designs corresponding to acceleration, those have been taken care of. There is no jump observed over here because it starts from a zero acceleration and it reaches once again to the zero value at the end of this displacement beta. Jerk is now there, but this is finite value that we can handle, so that's why it is not going to be that problematic over here as compared to the previous designs. So obviously we started from expression for acceleration and eventually found out expression for the displacement. And this expression, when observed, this is an equation of a cycloid. So that's why the term cycloidal design is used over here. Now, it fulfills the job. So it is a valid CAM design. Fulfills in a sense that the fundamental of CAM design is followed. You are going to find out continuous acceleration and jerk terms, and you have finite values assigned to them as well. But a little bit of concern arises corresponding to acceleration and velocity terms. And if I make you see that, for example, in the simplest example, force is equal to mass times the acceleration. So if acceleration value turns out to be higher than the other functions, then obviously the force required to run the CAM follower mechanism is going to be higher as well. And similarly for the velocity, if you recall that kinetic energy was equal to, for a single mass, it was something like that. So if velocity turns out to be higher, the squared of velocity is going to be further higher, which is going to have some concern raised for the kinetic energy required to run such systems. So as compared to other functions and as compared to other models of CAM design, the acceleration and velocity values are observed to be a bit higher. So that's why we're going to raise this a bit of concern over here, although the fundamental law of CAM design is completely followed over here. So with this realization that we have gradually improved the CAM design procedure, in a sense that we started from a naive CAM and then we moved on to have a simple harmonic motion exhibited, and then we observed its behavior and tried to find ways to further improve it, eventually reaching to the cycloidal CAM design, which is a reasonable, acceptable CAM design for us. And also we have raised a bit of concerns. We're going to try to address them in the subsequent discussions. But once again, we're going to raise this question over here. Can we do something more? Although this cycloidal CAM profile is an acceptable CAM profile, but we are going to, or we wish to further improve it, and that's why we are raising this question over here. And yes, we can do something more. And for that, we're going to consider the trapezoidal mode of action, specifically for the acceleration. But before we discuss that, just first consider what this constant acceleration is and how it behaves. So in this particular diagram that you can see, the acceleration is being shown on the vertical axis. So this is the acceleration, and you can see that there is no acceleration for the load dwell segment, and once the rise is there, the acceleration is going to quickly jump to the higher value. Now this step function is going to be problematic when you take the derivative to compute the jerk, and you can see that like infinite spike in the jerk profile is visible because of the sharp rise in the acceleration. And then on the other side, when it tries to fall down, quickly, you are going to find another spike corresponding to that. And when once again it rises up, with this rising edge, you're going to have another spike appearing on the jerk profile. So you can see that the constant acceleration gives infinite jerk spikes on the profile, which are going to be problematic. And from the observations that we have made earlier, as well as the fundamental law of CAM design, we should avoid it. So what is the method of avoidance? The method of avoidance can be to use potentially the trapezoidal acceleration mode, and that's right over here. You can see that in this case the acceleration term is appearing over here, but now it has been modified a little bit. You can see a little phase or subphase, should I say, spanned over beta over 8. In that, the acceleration gradually rises up. So this is a rising function corresponding to the acceleration. Then there is, in the middle, you have a constant acceleration right over here, and then it falls down, and then once again the constant acceleration, and then once again it rises up. Now, by doing that, you are going to have the same behavior exhibited, but now when you take the derivative of this acceleration to find the jerk, now rather than having the infinite jerk spikes over here, you're going to have a finite jerks appearing over here, corresponding to the subphases that we have mentioned earlier. So with this realization that trapezoidal mode of acceleration is going to be a bit better acceleration mode as compared to constant acceleration, because it avoids the infinite spikes in the jerk, we're going to try to use this concept in the next discussion. Now, once the trapezoidal acceleration has been explained, it is appropriate to mention the concept, which is what we call modified trapezoidal acceleration. And in that, we are going to follow a procedure, and the procedure is this. But rather than discussing it in a textual form, we're going to graphically show it. So the very first step that we're going to perform in this procedure is to have a sine wave selected, and this sine wave is spanned over beta by 2. It's generally, you have observed that we start from 0 and we go all the way to beta, but we are not going to go all the way to beta, but we're going to stop right in the middle of it. So this is something like you have a sine wave confined in this particular span. So this is going to be the first phase or first step. But in that, you are going to further subdivide the segments of the sine wave into segment A, which is the rising segment, segment B, which is the falling segment, C is still falling, but it is on the negative side, and then once again rising back to the 0 value for the D segment. So you have A, B, C, and D subsegments in this sine wave already mentioned. Now, in the second step, you are going to split it and spread over the beta phase or beta span that we have mentioned earlier. And you can see that happening over here. So you took the A and you placed it right over there. So this is A, this is B, this is C, this is D. But in between, when you spread from beta by 2 all the way to beta, you have this like the empty space and this another empty space over here. Now what we are going to do in the step C, which is already shown to you, in step C you're going to have the constant acceleration waveform shown, but now the segment E and segment F are going to be placed right in the middle, like in the empty spaces. So when you plug in these lighter shaded gray portions in the split sine wave, you are going to find out a combined waveform like this that you can see in step number D. So combining the two, you are going to have segment A connected with segment E, which is then connected with B, C, and then with F, eventually reaching to D, which once again brings the acceleration back to the zero value. And I should emphasize once again over here that we are still following the same procedure that we said, that we're going to start from the acceleration expression, and then we're going to integrate it once to have the velocity, and then another time to find out the expression for displacement. And we are going to take the same acceleration expression and take the derivative of in order to find out the jerk expression. So this is something like we are going to start from acceleration and build the SVAJ diagram around it. So we are going to follow the same procedure over here as well. But in this case, now what we have done is, like, we have merged the two waveforms together to construct a modified trapezoidal acceleration. And this is going to be helpful as indicated in the subsequent slides. When you plot the SVAJ diagram, you are going to have the acceleration, the modified trapezoid that we have discussed in detail, plotted right over here. So this is computed over here after the integration for the velocity, and then this is another integration for the S. So this is S, this is V, this is A, and then from here over here you have to take the derivative. So this is the jerk term. And obviously when you observe that the jerk values are, the maximum jerk values are finite over here, so this fulfills the fundamental law of cam design. And you can observe over here as well that the velocity starts from a zero value, it goes back to the zero value, and in between it rises to a specific Vmax. And for the follower displacement, you can see that it is kind of a continuous rising function. It rises up and in a very nice fashion up to the point that you wish it to achieve. In this case it is 1, but obviously you can specify it according to your requirements. So this is the SVAJ diagram of a modified trapezoidal cam design procedure, and we have reached to this conclusion after gradually improving by having the observations on the outputs of different cam design methods. So this is something like we have in a stepwise fashion performed this activity of improving the process one piece at a time. But still there can be further room for improvement, and one room for improvement can be like this, that rather than having a modified trapezoidal, you may have a modified sine as well. So in this case, what we're going to do over here is that we are going to start with a sine wave like this. This sine wave is similarly split into 4 segments, A, B, C, and D. And then you are going to have another sine wave over here in step number B, which is of a bigger wavelength. And then you are going to have the A, B, C, and D taken out in a similar fashion as well for the rise, fall, and on the negative side as well. So when you have the sine wave of period beta by 2 added with another sine wave of period 3 beta by 2, combining these two together, you're going to have the full beta reconstructed. So you're going to take the A segment from the shorter wavelength sine wave, which is A. You're going to take the D from the other side as well, from this side as well, and in between you're going to plug in the shaded gray wavelength sine wave, And when you combine them together, this is going to be your final shape. It rises up sharply and it falls down smoothly. Then in the last phases, it rises up once again. So when compared with the modified trapezoidal action, it performs relatively better as well, because it has got the lowest peak velocity, which means that the kinetic energy required to run this cam follower mechanism is going to be lower than the one experienced in case of modified trapezoid or cycloidal cam profiles. So in this gradual improvement fashion, we can find out ways to further improve the cam profiles, as we have done gradually in our case. So the cam functions that we have discussed so far belong to a particular family, what we call SCCA family. This corresponds with the sine, constant, cosine, acceleration. So this corresponds with the way we define the acceleration, and in that how we plug in the other expressions. So this is SCCA family, and in that we're going to perform certain comparisons in the next slides, but you're going to observe this kind of SVAJ diagram. So this is S, this is V, this is A, this is J. You're going to start from here, integrate once again to find V and S respectively, and take the time derivative or derivative with respect to displacement to find the jerk. So this is the RDFT cam design paradigm, which corresponds with the SCCA family. And in this family, if we compare the acceleration profile, you are going to find out all the curves mapped over each other like this. Now this diagram is important because it gives you the insight, and that's exactly what engineers aim for whenever they perform certain design activity. So the very first thing that you should observe is that you have the independent axis over here, which corresponds with the theta, and you have the dependent axis over here, which corresponds with the acceleration term over here. So in this particular case, the very first curve that we should start our discussion with is simple harmonic, like over here. So this is simple harmonic profile that we have available over here. So this goes, it starts from this value, and on the other side it goes all the way to this. So these are the two points from where the acceleration starts and acceleration finishes, and these are obviously finite non-zero values corresponding to acceleration. So when you take the derivative to find out jerk, this discontinuity is going to be adversarial in our case. It is not going to be helpful, because it is going to create infinite spikes on the jerk profile. So obviously this is not good, and we can see when compared with the others as well that this is actually is adversarial for the same reason. The other one that we should start discussing is cycloidal, and with that the parameters are indicated, and you can see that it starts from zero value right over here. It goes up, but now if you observe this cycloidal acceleration, when it goes up, it goes beyond the other profiles as well, and that's what was mentioned when we were discussing the cycloidal cam design, that the acceleration term is going to be higher. And what does that mean? It means that since acceleration is higher, so the force is going to be higher as well in order to make the follower move. So for that reason, if you attach a motor with that cam, or attach some engine or some driver with that, it is going to feel that it is exerting larger force as compared to some other designs that you have over here. If we take the other one, for example, there is this modified sine indicated right over here. You can readily see that the maximum acceleration is much lower than the acceleration observed on the cycloidal. So this is lower than the cycloidal acceleration. So that's good. But if you compare it with the modified trapezoidal, you can see that the modified trapezoidal has got the maximum acceleration to be a bit lower than the modified sine as well. So that's one advantage given to the modified trapezoid. In case of a design engineer finding it difficult to decide among different versions of the cam profiles, this kind of curve is going to be helpful in a sense that it is going to give the designer some deeper sense of understanding that which profile is going to create more forces when you try to move in case of acceleration. Another diagram can be used for the velocity to find out the velocity profile. We're going to see that in the next. So up to this point, we have covered these cam profiles right over here. This is part 1. And in the next lecture, we're going to cover the remaining ones. If you have any questions on the discussion that we have had, you can post them in the MS Teams group. I'll respond to those at the earliest.